question 22. First is that you should be able to identify where the question is coming from. So looking at question 22, the pressure of 1 mole of an ideal gas of volume 10 raised to the power of -2 meter cube at a temperature of 27 degrees Celsius is, so we're looking for the pressure. So you're given the molar gas constant. So obviously this question is coming from the general gas, the gas laws actually. So this is ideal gas equation. So from the ideal gas equation, you need to know the general formula. And general formula before is that PV is equal to NRT. PV is equal to NRT. So where P is equal to the pressure which may either be in atmosphere or Newton per meter square or meter per. But I'm going to tell us the particular pressure that is good to work with, depending on the unit of the general gas constant that you give. So your V, which is the volume, you may have that in GMQ or meter cube. The N, that is number of moles. Number of moles. R, which is now the general gas constant, which you have as 8.314 joule per mole Kelvin, or you have it as 0.082 ETA DMQ per mole. Okay. So these two values of K are actually the most common ones that you'll be working with. So YT, that is your temperature, a thermodynamic scale temperature. Temperature, you have Kelvin. That is, if you are given in centigrade scale, you have to convert to Fahrenheit scale. Yeah, so going back to that question quickly, you need to be able to identify each of these parameters when you get to the question. So from here, you can obviously see that the volume given, that is 10 raised to the power -2 meter cube. The given temperature you're given there, that is 27 degrees C. When you want to convert that to Kelvin, you add plus 273 to that. And that's going to give you what? It's going to give you 300 Kelvin. So that is that. And you see that the value of the general gas constant given is 8.3 joule per mole per Kelvin. So very quickly, depending on the value of the unit of your pressure and your volume, please. When you have, I'm going to circle them together. When you have units of your pressure in Newton per meter square, automatically you need to have units of your volume in meter cube, so that it will make sense to use this value of R as a general gas constant. So note the ones in red. Also, if you notice your pressure in atmosphere, that's ATM, your volume also needs to be in TM cube as well, so that the unit of R you're going to apply will be 0.0H2 ATM TM cube per mole per Kelvin. So please note that those in same colors work together. Have it together. Yes. So now let's get back to quickly to this question. So when we have this, we are looking for pressure, right? And it says 1 mole. So that means my N is equals to 1 mole, right? So to solve for that, we're going to do PV is equals to NRT, right? So let us quickly compute that here. So P is what we're looking for. So P is equals to, yes, NRT divided by volume. Yes, when simplify for that, N is 1 mole times 8.314. But from there, you actually given 8.3. So that's an approximated value times your temperature, which is 200 Kelvin, divided by your volume, that is 10 raised to power negative 2, right? So when you solve for this, what do we get? So there, you notice your value to be 249,000. What do you think the pressure will be there? So remember what we stated earlier. This will be in Newton per meter square, which is same thing as Pascal. Okay. So back to this. Okay, in standard form, bring this in standard form, you have 2.49 times 10 raised to power what? 1, 2, 3, 4, 5. And 10 power 5 Newton per meter square. Yes, you're good to go. Which is approximately 2.5. So moving away from that, okay, 10 by this. So definitely it's gonna be this one, right? But actually, when you look at the units there, the units might be something you want to put out. So why I want to believe that that's a mistake and help from there. So 23, which of the following has no effect on radiation? So which of the following has no effect on radiation? Option A, you have density, B, you have temperature, C, you have surface area, and D, you have nature of its surface. Well, very quickly, uh, we all know that radiation, as we can see here, is one of the means by which heat can be transferred. Yes. The other being convection. Oh, sorry. The other means of heat transfer being convection and conduction, right? Or let me just write the whole of the three quickly. Radiation. So please do note that this radiation that you see here, a very important formula you need to know under, radiation of a thing is this Steven Boltzmann equation of radiation, which you need to take note of. Steven Boltzmann equation for radiation, or Stefan's rather, Boltzmann equation for radiation. So from there, you might actually get some hints of some of the factors that that may affect radiation, right? So here, he say that the rate of heat transfer from a hot body to another body without passing through any particular medium, whereas rate of heat transfer Q over T is actually uh, directly proportional to the you're gonna have the area here, that proportional to the area, also that proportional to something we call of the material, emissivity of the material, emissivity, uh, thermodynamic temperature raised to the power of 4. Yes, such that when you want to remove this proportionality sign here, you're going to have Q over T is equal to, we now introduce the mass constant, Stefan plus mass constant. So you're going to have this symbol, this area, emissivity, C raised to the power of 4. So do not forget this guided is what we call the Stevens uh, Boltzmann constant, or the Stevens Boltzmann constant rather. And the value is about 5.67 celsius per negative 8 uh, watts per meter square per Kelvin to the power of 4. So that is that. Please do know that A is the area. Area of the surface usually you need to take note of that in meter square. This one here is emissivity, and the value of emissivity for a very perfectly black body is equal to 1. Emissivity of the material. Emissivity of the material just having to do with the measure of how well a body emits and absorbs radiation. Like T is the temperature. Please note that the temperature is in Kelvin. That's the thermodynamic scale. So from here, you know definitely that radiation definitely rate of radiation, which is definitely equals to power, is affected by something we call the, the area emissivity, which is based on which is actually the nature of the material. For example, a very perfectly black body is a best emitter and also a best absorber of heat, and also affected by temperature. So let's get back to the question. So when you look at this density, well, let's skip that for now. B, temperature, is part of the formula. C, surface area, also part of the formula. And D, uh, nature of the surface, yes, also part of the formula. So if I'm to denote them, this will be emissivity, this will be surface area, this will be my temperature. So definitely this is not part of them. So it's gonna be option A, right? So question 24. The wavelength of a wave traveling with a velocity 420 meter per second is 42 meter. What is its period? So definitely you must first identify that this question, where is it coming from? So where is it coming from? To be assured that the question is coming from a topic called wave in physics. A very quick one. Wave formula in physics, you need to know this, that wave, as far as wave is concerned, we must know the V equals to F lambda, which is talking about the wave speed, frequency, and the wavelength. So here, V is equals to the wave speed or the velocity. F is the frequency, right? This one will be in meter per seconds. This will be in per seconds or hertz, and this will be the wavelength. And do not forget the definition of the wavelength in wave. It stands between two successive crests of thrust. It should be in meters or centimeters, whatever the units you give. And yes, you have diagram like this, a diagram like this. You have a plot of wave. You have something goes like that, like that, like that, like that. Let me complete this here now. Yes, something like that. So this is a plot of y-axis against the x-axis. So usually you should know that on this y-axis measured in meters or centimeters whatsoever, y on the x-axis, that is direction of uh, propagation. This is the direction of propagation, as may have been found. Y up there is direction of vibration. So you know that this successive press, right? These are successive shock. Distance measured from here down to here, that is lambda. Here down to there, that is lambda. Right, from here, from this point to this point is one complete wave. Also from this point to this point is also a complete wave. So here I basically have two complete waves, right? So let's quickly move to that question so that we can move on from there. So wavelengths of a wave traveling. So yes, you have the wavelengths there. Wavelengths, yes, that is what 42 meters. 2 meters. You have the wave speed, that's the speed with which it is traveling with 420 meters per second. So what is this period? Yes, you know that period is the inverse of wave frequency. So V equals to F lambda. So you're going to have that F is equals to V over lambda, right? So definitely, if period is the inverse, period which is equals to 1 over F, period will be equals to lambda divided by wave speed. So let's quickly compute that. So that means that we want to solve for that now. If C is equals to lambda divided by wave speed, that is equal to what's the lambda again? You have that given to be 42. This one is 420. So this is definitely 0.1 seconds. So one of the goal is 0.1 seconds. So in fact, the sound of an electric bell dies down slowly when air is slowly pumped from a battery because so option A, you have sound cannot pass through the bottle. So B, sound cannot pass through a vacuum. C, sound needs a material medium. And D, the wavelength of the sound becomes greater in it. So obviously, uh, they say when air is fully pumped out from the bottle. So it definitely tells you that air is actually the material medium that is causing the sound to occur. Definitely, most likely, you have this option as your best answer. So sound needs a material medium. 26, during a thunderstorm, sound is heard over a long time. This phenomenon is known as yes. When you hear sound over a long time, you know the kind of sound that will occur after the source has been removed. So that is definitely uh vibration. 27, the velocity of sound in air at the same degree Celsius is 340. What will be what will it be when the pressure is doubled and its temperature raised to 127 degree Celsius? So first thing is that you want to be sure where is this pressure coming from. And the parameters you given also might point to what are the things like what are you actually working with. So temperature one, where were you? I will first start with temperature one, which is 16 degrees C, velocity one, that is 340 meters per second. What will it be when the pressure is double? So that means I have P2 equals to 2P1, yes, double, and temperature raised to 127 degrees Celsius. 127 degrees Celsius. So I need to convert this temperature to Kelvin. So we have this one plus 273. We have that to be 289 Kelvin. And we had this one plus 273. We have that to be 400 Kelvin, right? Yes. So how do we go about this? This question is actually coming from uh, sound waves. So you have to know some formulas that relate velocity and pressure together when it comes to sound waves, right? Okay. So velocity of sound there are some formulas. Uh, okay, instead of it's something you can actually use. What's it called now? It's something we can use the ID gas equation. Okay, I do not think so. So let's work with this formula that says V is equal to square root of uh, 3p over density. V is equal to square root of 3p over density. So you know that pressure and uh, from the ideal gas equation actually this can be equal to square root of 3. Okay, let's relate P quickly. You know, we have PV equals to NRT from the ideal gas equation. So which is PV is equal to mole is mass over molar mass, general gas constant, and T. So kind of when you bring in density there, you have P is equals to I want to bring this volume under this mass. So I'm going to have mass divided by volume divided by molecular mass RT, so that we can have that P is equals to density RT divided by M. The kind of relationship we are able to appreciate here is that pressure is that proportional to temperature, right? Yes. So which means that here I or if you in this equation here we appreciate pressure divided by density, right? Pressure divided by density is there in this equation. So it's something that we can try to work out for here, which shows that pressure divided by density is equals to RT divided by molecular mass of the gas. Oh, sorry. Okay. RT divided by molecular mass of the gas. So something I can just bring in here that gives 3 RT divided by molecular mass. Yes. So from here, kind of a direct equation that velocity of sound varies directly as the square root of the temperature considered, provided you know the general gas is constant R and also the molecular mass of the gas is also constant. So we can have that V1 divided by root T1 equals to V2 divided by root T2. Yes. So now uh what's the V1 given again? Yes, 340, which we've written out there. Pressure. Yes, we're not going to work with that as the formula has shown, which implies that pressure does not affect the speed of sound in air. So this is 340, temperature one is 289. So let's work with that quickly. So this is 340 square root of 289 is equals to V2 is what we're looking for, divided by square root of T2, that is 400. You know that this is 340 divided by 17 equals to V2 divided by this is 20, right? So it means that V2 equals to 20 times 340 divided by 17. So what do we have there? So that will give us 400 meters per second. So this goes there, that is 20. So 20 multiplied 20, you have 400 there. So that's question you have this as the right answer. 28. In comparing the camera and the human eye, the field of the camera function as so there's this acronym you can use to remember that. An acronym we used to use then. So that is trade ref. So P there, as is pupil is equivalent to the aperture camera. So those are together. The I, that is iris, I is equals to iris. You have D, that's the diaphragm. So those are relatable. So R the R is equals to the retina, and E. Oh, okay. So RE, rather retina, and then this, so F, that will be the film. So they are related together. Mm. So just try to remember those that acronym to be easy for you. So that's so the film, that will be retina. So remember page ref 29. So an object 4 centimeter high is placed 15 centimeter from a concave mirror of focal length 5 centimeters. So the size of the image is, so you can see this is coming from mirror in physics, because concave mirror was mentioned. So the object height, as height of the object, that is 4 centimeters, is placed 15 centimeter, that is distance of object, that's 15 centimeters. Of focal length, yes, you have focal length given there, that is 5 centimeters. So you want to look for the size of the image. Size of the image, of course, that will be height of the image, right? Yes, something like this. So when you have all of this, let's get to formulas for uh mirror quickly. When you have focal length involved, you have 1 over the focal length equals to 1 over the image distance plus 1 over the object distance. Since it is stated that it is a concave mirror, you expect everything here to be positive actually. But if it should be convex mirror, you might be having some negatives there, especially the image distance, which is always formed behind the mirror. So you also have the fact that magnification is equals to the height of image divided by the height of the object, which is also equivalent to distance of image by distance of object. In my identification, I use DI divided by D not there. So let's look at what we're given in the question again. So height of image 4, distance of object 15, F is 5 centimeters. So you want to look for a way of how you can get this height of image. So from here, uh, height of image can easily be gotten from magnification. That is, if you are able to solve that for magnification, already you know your height of objects, right? So let me just write them out here, kind of. Height of objects was given to be 4 centimeters. So remember you give it focal length. So definitely you have something to do with this equation here. So if I want to bring out magnification here, magnification is this here, right? And I'm given another parameter that I can work with. You're given distance of objects, that is u. You're giving it to be 15. So u, distance of object, which is u, equals to 15 centimeters. So you need to find a way of making sure you still retain u in this formula, and you find a way of bringing in m into that formula. So what will I do to this equation here? What I'll do to that equation is that I'll simply multiply through by u. So when I multiply through by u, that equation tends to be U divided by F is equals to U over V plus U over U. And that gives U over F is equals to, this will be inverse of magnification, then you have 1 here, right? So U there, that is 15. F there, that is, F is what again? F is 5. So F is 5 is equals to the inverse of multiplication you have there plus 1. So this you have 15 divided by this, you have 3 is equals to over n plus 1. So this cross to the other side, you have 2 is equals to 1 over n. From here, n equals to 1 over 2, which is equals to 0.5. So if m is equals to 0.5, let's see how we're going to solve for this guy here. So you can see there that height of image is equals to magnification multiplied with, yes, you're going to multiply this guy. Magnification multiplied with height of object. And that is 0.5 multiplied with height of object again. The height of object given was 4. Here was 4. So this gives us 2 centimeters. So that is 2 there. So go with 2. Question 30. An object is embedded in a block of ice 10 centimeters below the plane surface. If the effective index of the ice is 1.5, the apparent depth of the object below the surface is. So this is coming from real depth and apparent depth. It is related to the refractive index. So that 10 centimeters below the plane surface, that is likely to be your real depth. So it implies that your real depth is equal to 10 centimeters. Refractive index, you have that given to be 1.5, and you have you're looking for apparent depth actually A. So there's this relationship between real depth and apparent depth. So okay, so let's look at that quickly. You have there are two formulas that you need to know as far as this is concerned. Refractive index is equals to real depth, that's real depth divided by the apparent depth. Apparent depth. And you also need to know that thickness equals to the real depth minus the apparent. The real depth minus the apparent. So again, we are looking for the apparent depth. We are given the effective index equals to 1.5, and we are given the real depth equal to 10 centimeters. So when you look at it, how can we solve for apparent? So it is obvious. Oh, okay. So I meant this to be what's it called? Displacement. Let me clean that quickly. So this should be displacement. So going to use method D there. This is R and this we use A. So if displacement is equal to real depth minus apparent depth, please note that this same formula can be equal to, that's in letter representation, real minus A, and if we, so as I've mentioned earlier, that displacement is equal to real depth minus apparent depth, as you can see, and using letter representation, real depth is how and apparent depth is A. So here I'm going to make apparent depth is always a formula there. So which means that you're going to have apparent depth A is equals to field depth divided by the refractive index. Please also know that this field depth is also called the thickness. So that when we bring it in here, we're going to have field depth minus reference to this place minus r over this is what the displacement d, such that you can have that d is equals to, when you factorize that r into bracket 1 minus 1 over the refractive index. So don't forget that r can also be called thickness. Okay. So now back to that question quickly. It happens to be that the parameters we given are very straightforward. So you are just simply working with this particular formula here that you have. Okay. So that is working with that formula. Refractive index is equals to r over a. I'm looking for a. A is equals to r over refractive index. My a is what I'm looking for. R is 10 divided by refractive index, that's 1.5, which is 3 over 2, right? So that will be 10 times 2 divided by 3. So this is 10 divided by 3. You have 6.66 centimeters as the unit is concerned. So 6.6, I believe this is probably a mistake here. The value cannot get up to 67 centimeters in this question. So that's 6.67 or 6.7. So 31, which of the following is used for the correction of short-sightedness? Well, short-sightedness, we go with, okay, so convex lens is a diverging lens. It's not, or is it? So diverging lens, you have it this way. It's the edges of like this. While the convex lens, you have it this way. This is a converging lens, meaning that any rays that you have coming from the edge come to converge, come to edge, come to converge. And it simply implies that most likely the normal lens has been, the rays has been getting beyond where it's meant to stop. Do you understand? So if you are using a converging lens, you want the rays to converge as much as possible to a more nearer point. So that means that this will be long-sightedness, as the case may be. This will be for long-sightedness, for correction of long-sightedness, because the rays is initially going further than where we want it to be. So this is the concave lens, which is diverging. So initially, the rays was probably, converging at a point that is very near. It doesn't really got into the main point on the retina. So we need to converge it to get to where it's going to. So you go with option A. 32. Dispersion occurs when white light passes through a glass prism because of yes, one thing you need to know about dispersion is that different colors of white light, that is Roy wave, they travel with different speeds. Different speeds. Okay. So different speeds, and as a result, so 32. Dispersion occurs when white light passes through a glass prism because of the A, you have different speeds of the colors of the glass. B, you have high density of glass, defects in glass, and different hidden colors in the glass. So when you look at the options very well, one thing about this exam also is that you try to eliminate options. So C and D are not actually making sense like that. So you are left with A and B. So A, different speeds of the colors in the glass. The color is Roygbiv, right? ROYGBIV. And they all, of course, travel with the same speed. That is speed of light, 3.0 times 10 raised to the power 8 meters per second. So it can't be possible that they travel with different speeds. Definitely, it's most likely going to be high density of the glass. And it makes sense. The high density of the glass, or how well packed the glass molecules are, is what is responsible for the scattering of the white light, which is resulting to dispersion. So 33, When a positive charge rod is brought near the cap of a positively charged electroscope, the Leibniz divergence will, of course, you expect divergence to increase more. When you bring similar charges together, they're gonna repel. So it's the divergence increases more. So you expect it to diverge. 34. Three capacitors of capacitance 2 microfarad, 4 microfarad, 8 microfarad are connected in parallel, and a potential difference 6 is maintained across each capacitor. The total energy is what? So quickly, let's solve that on this page. Three capacitors, when capacitors are connected in parallel, you add them together. C in parallel. That is 2 plus 4 plus 8. So this gives 14 microfarad. And the given voltage is what? 6 voltage. So we're looking for the energy, total energy. So total energy as related to capacitance and the voltage is half CV squared, which is half multiplied with the C. That is 14 times 10 to the power negative 6 times V squared. That is 6 squared. So quickly, 2 divides 14, you have 7. And then 6 squared, that is 36. 36 multiplied with 7. So you have, that is 252. E is equals to 252 times 10 to the power negative 6 joules. And by indices, it is 2.52 exponential negative 4 joules. So you expect this one to be your correct answer there. 35. A set of EMF 12 volts and internal resistance 4 ohms is connected to an external resistor of 2 ohms. Find the current flow. This is coming from current electricity. Yes. So you need to know this relationship that E, sorry, that I is equals to E over R. E over R. So that is for a normal cell when no external load or when no external resistor is being attached. When you have an external load or external resistor attached, it becomes that I is equals to E over the external resistor and the internal resistance. So this gives your EMF, that is 12 volts. So 12 divided by external plus, so internal plus external, that's 4 plus 2. That is 12 divided by 6, and you have 2 ampere there. So you expect option B to be your correct answer. 36. The diagram above shows the balance meter bridge in the value. Okay, the diagram above shows the balance meter bridge. The value of X is, so this is a meter bridge where the resistance corresponding to the length at which you place the jockey. So it implies that this all of the combination of these two resistance which are in parallel is against this value of X, and the 8 ohms here is against this distance 100 minus X. So the equivalent of 8 and 8, that will give, let's quickly calculate for that. For resistors in parallel, R total is equals to R1 R2 over R1 plus R2. So you have that to be 8 times 8 divided by 8 plus 8. That's a 64 divided by 16. And you have that to be 4 ohms, right? So that means 4 against X. So you want to be sure that the EMF is that proportional to the length as the case may be here. So that A1 over L1 is equals to E2 over L2. So what is the E1 in this case? We've calculated the first one there, that is 4. So 4 divided by L1, that is X, is equals to E2, that is 8 divided by the other distance there, 100 minus X. So when you cross multiply, you're going to have 4 into bracket. 100 minus X is equals to 8X. It gives 400 minus 4X is equals to 8X. So at the end of the day, you're going to have 12X is equals to 400. So that X can be equals to, we have 400 divided by 12. So that will be 33, 33.3 centimeters. So very close one there. And you have a C. Okay.